Okay, we're back again. Sorry for the 5-minute delay. We will carry on with the so-called exercises. In this case, we refer to an exercise which makes reference to a comparison between an oil-fueled and an energy-fueled operation with the example of a Greek island ferry, which is very close to what might be considered as relevant to this seminar, since it makes reference to an alternative fuel such as liquefied natural gas. Okay, this is true for all island regions. I would say for most coastal regions as well, as it was already mentioned in the previous cases when we were talking about freight transport. It is important to make sure that sustainability does not only involve commercial viability of a service, but it should look at the aspects of safety as well, but most importantly the friendliness of the service with regard to the environment. Now, within this requirement for environmentally friendly services, exhaust emissions, as it has already been mentioned, are very important for shipping operations which take place very close to islands on mainland coasts, and as well as ports, and therefore is something we should look at. Now, with reference to Greece, we have to acknowledge the presence of a very high coastal shipping activity within the Greek seas. And when we say coastal, it refers mainly to coastal passenger shipping, in other words, ferry boats and ferry services, but of course there is also freight, coastal freight, but which operates in line with passenger shipping as well. But the dominant presence of passenger coastal shipping is evident, and is a case which should be looked at with particular attention because of the environmental sensitivity of the Greek islands. Now, in order to choose the so-called greener fuels for coastal shipping instead of oil fuels for powering of island ferries, it's always necessary to embark on a techno-economic analysis which will provide a comparison of the associated costs and benefits. And this is the case in this current exercise. You have to choose one of the two videos. Somebody send a message. You have to choose one of the two videos, Thanos. Somebody send a message. We have to choose one of the two videos. Ah, that was you. Okay. Okay, thank you. Now, a description, a schematic presentation, a description of the ferry itinerary we're looking at is shown here. Is a connection between Piraeus and Rhodes. It involves the immediate connections to the island of Syros, Astipalea, Nisyros, Tilos, Simeon roads. It is a busy route, and we chose that as well on the basis there is a pretty lengthy itinerary, which will give us some sort of illustration of how conventional oil fuels compare to an LNG operation of this particular ferry. The ROPAX employed in this operation is got a service speed of 20 knots. The duration of the overall trip is 18.3 hours, which is divided in roughly 16 hours at sea time and 2.5 hours of port time, equally distributed, 30 minutes at each of the 5 intermediate ports, as shown in the figure above. And it involves a stoppage time of nearly 5.7 hours on either of the end ports, meaning Piraeus and Rhodes, which we consider as the main ports involved in this line. Ferry does one trip in each direction every day. Therefore, with the allocation of 30 days for dry docking, the ferry performs 335 trips in a year. With regard to the ferry characteristics, what is important to know for the purposes of this exercise, because the ferry has a lot of features, technical and operational, but it might be important to state that we have a gross tonnage of around 10,000 tons, got an overall length of 140 meters, propulsion power requirement of 12,000 kilowatts, with regard to the maximum continuous rating, which is shared by two propulsion engines. So we're talking in terms of having a twin screw vessel, as it is the case for all ROPAXes operating within the Greek coastal shipping network. This is a national regulation requirement. The auxiliary power requirements of 300 and 500 kilowatts are provided by 4 electricity generators. These are the basic characteristics which are essential for the exercise. In other words, main engine sizing and auxiliary engine sizing. As it was mentioned in the previous presentation, an activity-based methodology for fuel cost estimation is chosen. We split the fuel costs as those which the ROPAX will present during its operation at sea and in port. Okay, and to that extent we need a number of itineraries in order to have an annual estimation of the fuel costs. We need the trips per year. We need also the time of operation of the main engine and the auxiliary engines, either at sea and also at sea and in port, which we will have to connect with specific fuel consumptions for the main engine and the auxiliary engines, as well as effective load factors for the engines, which is a combination of the percentage of time the main engine or the auxiliary engine, whether at sea or in port, operates at a specific load factor, together with the price of fuel, which we will have to distinguish between the fuel used for the main engines and the fuel used by the auxiliary engines. And here are all the assumptions with regard to this specific itinerary. Sailing distance per trip is around 316 nautical miles, which is a long distance, even for within the framework of the Greek coastal shipping network. And we get some further details with regard to what assumptions are made. Now, with regard to the fuel cost price, we will see that we're talking in terms of nearly 500 euros per ton for a low sulfur fuel oil operation and 722 euros per ton for distillate. And the price of natural gas is almost half of that of distillate. Now, as it is the case we're currently experiencing, these are not typical prices, but the differences in the price of oil and the price of natural gas more or less the same, remains the same. So in absolute terms, we might encounter some variations with regard to what is happening today, but in terms of comparison, there's no great difference involved. Now, the benefits of the activity-based methodology are also utilized in order to estimate the air pollution cost of the service. Again, we separated between what we have at sea and what we get in port, because the damages are not the same whether you are away from a port or whether you are within a port, especially if that port presents some sizable human population. It is particularly vulnerable to emissions, to exhaust emissions, and to be more specific as well, to particulate matter. And with regard to that, the assumptions we do are listed here on the right. The emission factors, again, come from reliable sources from the literature. With regard to low sulfur operation, which this ship has to have, as it is a passenger ship which is operating on a regular basis between European ports, and of course the conditions of reduced sulfur content apply. This is in contrary to what was mentioned earlier today with regard to a ro-ro vessel, which belongs to within the category of a freight vessel. Also, we have to come up with external cost factors, and it is important to note again that we have a very high influence of the damages of particular matter, the emissions in particular matter, because of their impact upon the human population, pulmonary diseases and all the problems associated with their inhalation by human beings residing or having a presence within the ports of call of this service. Okay, so we do assume maximum that the ROPAX operates with regard to the fuel used by the main engines on an oil fuel which has a maximum sulfur content of 1.5%. And then with regard to marine diesel oil, which is usually employed in diesel electricity generators, the sulfur goes down to 0.1%, which is more or less a desulfurized fuel, and for that reason we have reduced emissions of sulfur dioxide and particulate matter, because these two, as it was mentioned earlier in the day, they're very much related in comparison to what the emissions of the fuel of 1.5% sulfur are. As you can see, the difference is quite significant. Assuming all other emissions with regard to NOx and CO2 are unchanged and are irrelevant to the sulfur content. Now, we need some specific fuel consumption factors as expressed in grams per kilowatt hours, and we can see what the consumption of the main engines are at sea and in port, and also the consumption of the auxiliary engines. In other words, the diesel electricity generators are, whether they are at sea and in port, they are the same. With regard to the engine effective load factors, okay, the engines operate at a certain load factor. When at sea, we are operating around 75. In this case, it is assumed is 80%. With regard to MCR of the main engine power for 100% of the time. So an effective load factor of 0.8, we have this estimation, and similarly, when we are at sea, with regard to the electricity generator, we operate at 30%, 30% of its power for 100% of the time, which gives us an effective load factor for the engine of 0.3. In ports, in main ports, as it's always the case with activity-based exercises, we have to consider that we're having an approach phase and a maneuvering phase and a berthing phase, okay? And we have a load factor of 0% for 80% of the time with regard to main engine in ports, but we also recognize that for 20% of the time the main engines will operate at 20%. It gives us an overall engine effective load factor of 0.04. Similarly, for the electricity generators of the ROPAX vessel, we can see that for most of the time they operate when they are in ports, in the main ports. This is the operation in the main ports. For 80% we will operate at 20%, and for 20% of the time we will operate at 60%. Okay, this is to cater for making allowance for hoteling requirements during the year, in terms of air conditioning, as well as maneuvering. Both thrusters do take a lot of electricity load during maneuvering of the ship in and out of the ports. And finally, with regard to small ports, again we have some load factor percentage of time. 20% of the time, 100% of the time we operate at 20%. The main engines, and 100% of the time they operate at 60%. With regard to auxiliary engines, and giving us correspondingly engine effective load factors of 0.2 and 0.6, towards a significant variation to what happens between in main ports and in small ports, where the ship does not really rest or as such for long periods of time, like when the RoPax is at Piraeus or in Rhodes, and it has to wait for a few hours before it starts its journey. It's apparent that the main engines will not operate for a long period of time. But the same might apply to a certain extent to the diesel generators, as opposed to what is happening in the intermediate ports, where we still have to carry on operating and supporting the ferry in terms of its main engine operation and auxiliary engine operation for the short period of time we are spending in the small ports during this itinerary. Now, with regard to the unit cost of exhaust pollutants, fuel and shipboard power technology, this is important because our assessment in terms of how the oil fuel operation compares to the LNG operation, we need to have unit costs for the air pollution, for fuel costs, and also for technical costs. And as you can see, there is a clear division between the unit cost of SO2 and PM, sulfur dioxide in particular matter, whether we operate at sea or in small ports. We consider the impact to be more or less similar. But in the case of main ports like Piraeus and Rhodes, because of the presence of human population, we can see that the increase in the unit cost of particular matter, or moving from being at sea or in small ports to main ports like Piraeus and Rhodes, is fivefold, 5 times more, where with regard to SO2, we have something like a doubling of the cost, twice. In other words, it increases by 100%, a bit more, SO2, where with regard to NOx, which has an effect which is not very critical to the human health, is more or less equal. Okay. Now, as I said before, we have some base scenario with regard to fuel costs, on which this exercise has been performed, and it wasn't performed in these days, but it's going back about a year and a half. We can see what the prices stood, at what levels the prices stood at the time. Now, with regard to the technical costs, this is the cost of the engine and all the installation, purchase and installation costs of the two powering systems, an oil, fuel oil or oil-fueled power system, and a good approximation is of €400 per kilowatt, where with regard to LNG, this is nearly double. The price is nearly double, is of the order of €700 per kilowatt. Okay. Now, the fuel costs of the oil and LNG fuel ferry service on an annual basis in million euros, we can see what it stands like, and we can see that the total cost of the oil ferry is more or less double than that of the LNG ferry in terms of fuel cost. And this is equally distributed between operating at sea and in ports. Yes, we'll expect that. So, okay, although it looks like the imports about 10%, the improvement is about 10% better. It's increased by 10%. In other words, 48% reduction in fuel cost due to LNG use and 58% in ports. Okay, but overall, we're around to 50%, as I said, more or less half of the fuel expenditure when operating with an LNG ferry. Exhaust pollution costs when we look at SO2 here and NOx. The benefits here are overwhelmingly high. We have massive reductions at sea and in ports, and overall we are moving around 90% reduction in air pollution costs, and this is very, very important. I just want to go back to this, look at what is happening. 7.5 million euros is the exhaust pollution cost per year, €1 million for the three species, SOx, NOx and PMs, when more or less this is the case of annual costs as well. So the fuel of the annual costs of fuels. So fuel costs and air pollution costs more or less equal. This is very interesting indeed, and something to be thought of. Whereas in the case of LNG, okay, we might still have about 3.7 million euro expenditure in fuel costs, but we only have 800,000 euros in terms of air pollution damage on an annual basis. In terms of an overall comparison of private, external and total costs of oil and LNG fueled ferry, as we can see, the oil ferry for 7.4, the external being 0.8, okay. Sorry, 7.4, 0.8 and minus 6.64 is the final improvement of 6.64 million euros is in favor of the LNG in terms of external costs, in terms of fuel costs, as well as technical costs. In other words, the purchase of the power system, capitalization costs of the power systems. We're looking at something like 3.3 million euro reduction over the year, and the total, in other words, external and internal, or call it private in this case, costs, will see that the LNG ferry for this particular line operates favorably by almost 10 million a year. When both, as I said, external and internal costs are considered, where with regard to internal we consider fuel costs and the power system. Okay, so overall nearly 66% reduction in costs in terms of from moving from an oil fuel operation to an LNG fuel operation. Okay, air pollution, 90% advantage. Fuel cost, fuel nearly 50% advantage. And with regard to technical costs, of course, we have an increase of the purchase and installation for this system is of the order of 75%, but overall the result is in favor of the LNG fueled ferry. Now, knowing that we have volatility in the in bunker prices, it was considered appropriate to look at different scenarios with regard to the LNG, with regard to low sulfur fuel oil and marine diesel oil prices. That's assuming, of course, that the LNG price remains unchanged. Okay, we do know that there is some linkage between natural gas prices and petroleum prices, but any such variation between the fuel price, oil fuel prices, and LNG can be accounted for through looking by looking through a ratio of LNG to MDO prices and then LNG to low sulfur fuel oil prices. Mrs. Nassau, okay, which can look at that. Ranging from a scenario which gives us an LNG to MDO price of 0.9 down to 0.45, like to 50% difference to that between scenario A and scenario E, and change between LNG to LSFO to low sulfur fuel oil, which can range over a factor of 3. In other words, we have a scenario A standing at an LNG to LSFO price ratio of 1.83 down to 0.61. And we can see how this relates. All the scenarios in terms of of their influence on fuel costs shown in this table. Let's look again. All the scenarios are in favor of the LNG, apart from the first scenario. It has the lowest fuel oil price and marine diesel oil price. Okay. All the other scenarios are in favor of the LNG operation, and they give us the difference between the two cases. Also, the price ratio of 1.5 gives us more or less an equal result with regard to fuel costs. But then on everything else represents a reduction in fuel costs, and that's very encouraging. Conclusions. The overall annual costs of the LNG ferry are about 66% lower than those of the oil fuel alternative, and the contribution of the private fuel and technical costs is lower than 43%. Okay. The fluctuations in fuel prices are not likely to reverse the comparative picture in terms of private costs, because as it was already mentioned, and unlike the approach adopted here, the natural gas prices usually follow the trends of the petroleum price. In terms of comparison, it's not likely to make any difference. Now, with regard to technical costs, in other words, the cost of purchase and installation of propulsion engines, it is important to know that in this case we're looking at the gas engine alternative only. Okay, in other words, we're not looking at having a dual fuel engine. For the power requirements of this particular service, we do have engines, especially where in the twin engine arrangement, which can cover this requirement, and these are pure gas engines, in other words, spark ignition engines. Because this is a problem about talking about trying to look at an exercise which involves the operation of gas engines beyond certain levels of power requirements. These engines are not available currently. But in this case, the market provides us with this option to use gas-only engines. Now, we can argue that the technical costs of gas engines, especially with regard to purchase, okay, the installation costs can remain the same, more or less, but purchasing such engines can become a much cheaper option as the production of this type of engines widens, and therefore the costs of the market through the market expansion will be reduced. So we look forward to having a better comparison of LNG propulsion, LNG-based propulsion in the future than we currently have. As in the market will have to expand and become more competitive. Okay. Plus the knowledge of in terms of operational costs, maintenance, repairs, or other operational costs related to this type of technology are expected to be reduced in the future as the knowledge of operation with regard to these engines will become more broad. Okay. Now the main advantage of using the LNG ferry, of course, is through the reduction of exhaust pollution. In this case, it goes down to 90%. And we do know that when it comes to shipping, this is an area of externalities, of negative externalities, where shipping currently has a problem because of the specification of marine fuels. A lot has to be done in order to bring it down to better levels, especially with regard to sulfur content of the marine fuels. This is not the case everywhere, as we know, and unfortunately the Mediterranean is not an emission control area, so we still have to suffer from the effects of using, even at the passenger shipping domain, within the passenger shipping domain, specifications which can further be reduced in terms of their sulfur content, but of course you can bypass that by choosing sulfur-free fuels such as natural gas, which is the case in this exercise. As provided, of course, the costs of the fuel are favorable too. Okay, so I would like to thank you for participating in this, attending this presentation, and if you have any questions, I'm very happy to answer. Thank you very much. Could you please upload? Okay. I'll upload the presentation.
Yeah, the presentation of the first session have already been uploaded, and I will now upload the presentation of the second session.